Welcome back to Very Ordinary Differential Equations. In this video, we'll learn about separable equations. Well, a first-order differential equation is called separable if it can be rewritten in the following way. A function of y times y prime is equal to a function of x. Now, this is a very specific form for a differential equation to take. On one side, you have only the variable y, but not the variable x. Well, on the other, you have only the variable x and not the variable y. Furthermore, the side that has your variable y, there's a y prime that can be factored out completely. And of course, x versus y is not important. What's important is that y is a function of x, whatever the letters might be. Now, this is a very specific thing. All of your independent variables on one side, all of your dependent variables on the other, with the derivative being able to be factored out. But we will see shortly it's a typically easy sort of problem to solve. Therefore, it's usually worth checking if a given equation is separable. Most of them won't be, but when they are, they tend to be a pretty quick solution. So let's suppose you have a separable equation. Here it is, h of y times y prime equals g of x. Well, how do we solve it? Implicitly, y is a function of x. So what we have here is h of a function of x times its derivative is equal to g of x. Now on the left, we've got the chain rule. Okay, so suppose that h and g are functions, so that capital H prime is little h and capital G prime is little g. So by the chain rule, the left is just the derivative of h of f of x, and on the right, we have the derivative of capital G of x. So this is what our equation now looks like. And by anti-differentiating, we can just go right back to the functions capital H and capital G by introducing a constant of integration. And then we can plug back in our original y instead of f of x. Basically, if you can separate an equation to look like this, all you have to do is anti-differentiate the function h and anti-differentiate the function g, and you're good. So it really turns out to just be two independent sort of single variable calculus integrals. Okay, so we can then maybe solve for y. Now this is actually a technique we've already used before. Specifically, we used separation of variables to solve linear first-order homogeneous differential equations. Those are those things of the form y prime plus p of xy equals 0, which we rearranged as y prime over y equals minus p of x. Now on the left, we have 1 over y times y prime. Okay, so this left side can be written as 1 over y times y prime. So we'll let h of y be 1 over y. And on the right, we have minus p of x. So there's our function g of x. So on the left, we have 1 over y times y prime, which can be anti-differentiated to just log y. And on the right, whatever the antiderivative of that function little p is, it has antiderivative capital P. And that gives us that log y equals minus p of x, and we can solve that for y by exponentiating. And we get e to the minus capital P of x, which we already used. Okay, this was our general format to solve linear first-order homogeneous differential equations, and we actually did it through separation of variables. So let's review this technique. If you can, and you generally won't be able to, but if you can, rewrite your first-order differential equation in the following form: a function of y times y prime equals a function of x. Well, integrate both sides, and there you have it. Capital H of y equals capital G of x plus some constant of integration. And depending on the form of that function capital H, you may be able to solve for y. Well, let's see an example. Let's solve the differential equation y prime equals 2 plus x squared times 1 minus y. Dividing both sides by 1 minus y will get us into this separated form. On the left, we'll have y prime over 1 minus y, and on the right, 2 plus x squared. Notice the left is now entirely a function of y, and the y prime can be factored out. We have 1 over 1 minus y times y prime, and the right is a function entirely of x. So we can integrate both sides. On the left, it integrates as negative log of 1 minus y, and on the right, it integrates as 2x plus x cubed over 3 plus c. Now, a lot of people would ask, why do I not need some sort of constant of integration on this side here? Well, if I put something like plus d on this side, and I introduce a constant of integration on both, If I then subtract it over to that side there, we now just have some alternate constant, c minus d, and that's really still just a constant, and why not just call it plus c? So it's really not very common to have a constant of integration on both sides. It's just not necessary. So get rid of it. Okay, we only need a constant of integration on one side. Now we can solve for y. Okay, so if you solve for y, you just have to multiply both sides by -1, then exponentiate, then multiply both sides by -1, and take the resulting -1 and add it over here. And you'll get this form right there. Y is negative e to the minus 2x minus x cubed over 3 minus the constant c, all plus 1. Now, when you have constants of integration inside exponents, okay, here our constants of integration end up in an exponential. Typically, this will be rewritten as a constant out here. Now, this is just because we have negative e to a bunch of stuff involving x minus c. I can rewrite this as negative e to all of that times e to the minus c. And e to the minus c is just a constant, and we can just call it a. Okay, so when you have a constant of integration being added or subtracted in an exponent, it will typically be written as a constant times that exponential. Okay, so this capital A, it's just another constant. That's fine. And this is a more typical way to present the solution. And here we have it, a function of x. Y is a function of x, and this solves the differential equation of the problem. Another example, let's solve the initial value problem. Y prime is, ooh, this looks like a mess, 2x plus cos x all over y plus 1. And our initial value is that y of 0 is equal to 2. Well, we can separate by multiplying both sides by y plus 1. So now we have y plus 1 times y prime, very clearly a function of y with a derivative y prime factored out. And on the right, we have 2x plus cos x. Can we anti-differentiate both sides? Yep, y squared over 2 plus y equals x squared plus the sine of x plus some constant. Now our initial value problem says when I plug in x equals 0, we should get out y equals 2. So if I plug in x equals 0 and y equals 2, we get 2 squared over 2, that's 2, plus 2, 4, equals 0 plus 0, so c equals 4. So implicitly, our problem is solved by y squared over 2 plus y equals x squared plus the sine of x plus 4. As another example, let's solve y prime times the secant of x plus the cosecant of y times x equals 0. And again, this is separable. Okay, so if we rewrite the secant of x as 1 over cos x, this would become y prime over cos x. And here I would have x over the sine of y equals 0. Multiply everything by the sine of y to get sine y prime, cancel that out. Now multiply everything by cos x, cancels this out, and you get cos x right there. Move this to the other side, and here we have it. Sine of y times y prime equals minus cos of x times x. So there is our separation of variables. Now we can integrate both sides. Minus cos y equals, now on the right we have an x times a cosine of x. This can be integrated. You would typically use a integration by parts to accomplish this, or just refer to a table of integrals, and you'll have a negative cos x minus x sine x plus some constant. Okay, multiplying both sides by -1, notice that a negative constant and a positive constant, they're really just constants, so I didn't bother changing my c into a minus c. Then I can solve for y by saying that y is the arc cosine of the cosine of x plus x cos x plus some constant c. So what have we learned? When a differential equation can be rewritten in the following form, function of y times y prime equals function of x. Notice the left, all of your y's, on the right, all of your x's, and the y prime on the left can be factored out. Then you just have to integrate both sides to get h of y equals g of x plus c, where those are antiderivatives of h and little g. Then, if it is possible to solve for y, it's generally desired to do so. Then you'll just have y equals something, but sometimes you'll just have an implicit solution where there's a function of y on the left. Now, this technique reduces a first-order differential equation to just evaluating two different Calc 1 integrals. Okay, and that's great because that's something we already know how to do. However, it will be fairly rare for something to work out so nicely. But because it's a pretty easy technique, and it's a short and direct solution, it's generally worth checking, hey, is this problem separable? If it is, great, it's now quick to solve, and if it isn't, it's generally pretty quick to see that it's not going to be separable.